at Ehrenborg who made me change my mind. I used to think that analysis, especially modern functional analysis, is completely useless, but now he found a beautiful application to something that I really like, enumeration. So I'm really looking forward to his talk. Richard Ehrenborg.
Thank you much, Dora. So let's begin with the combinatorics part. Maybe I'm interested in, well, I'm sorry. Actually, this is joint work with Sergei Kitaev and Peter Perry. Sergei Kitaev is the University of Reykjavik in Iceland, but he's moving, I think, this coming summer to Glasgow, Scotland, and Peter Perry is at University of Kentucky. So I'm interested in number of permutations I in the symmetric group on n elements such that there is no index I. So if I look at 3 consecutive entries, the permutation is increasing in these entries. So I would like to have no double ascents. Well, this is of course a combinatorial problem, but let's make it a geometrical problem. Namely, let X be the subset of the unit cube in n dimensions such that there is no index I, so that xi is less than xi plus 1 less than xi plus 2. So it's the same condition, except now I'm talking about vectors in n-dimensional space in the unit cube. And I claim that the volume, n-dimensional volume of X, is given by alpha n over n factorial. And you can actually see this. You take, here's the 3-dimensional unit cube, and you cut it by all the hyperplanes xi to the xj. That's all happening from the origin here, and that cuts the thing into 6 pieces. In general, the n factorial simplices. So the simplices, okay, well, now Dora, you know why I can't have my kids here, because this is not my toy. It's their toy. We steal it from them. So this is how the simplices look like. And since all the simplices are symmetric, you know, they all have volume 1 over n factorial. So that's the factor there. And that means that each of these simplices corresponds now to one is permutation and is what. So the question is then to compute the volume of this set. Well, this set, the n equal to 3, is what's left of this cube. And you see it's not a very nice set to look at. I mean, this is being cut out. So we had to do something else in order to study this problem. So the next thing is to say, well, we can define the corresponding 0,1 function. The function is 0 if there is a double ascent and 1 otherwise. Well, it's clear that then we have that this expression then is just be integrating of the n-dimensional unit cube of the 0,1 function. But to integrate with this set is not a nice thing, okay? This is what you don't want to give to your Calc 3 students. So, yeah. However, this hook now, what we could do instead is define the following function, fn, in terms of the 2 last variables. Namely, I'm going to integrate away over all the other variables, this n minus 2 of those, of this function Kn, x1 through xn minus 2. No, the function is still of the xn, dx1 over to dx minus 2. Question is, can I get my hands on this function? If I can get this function, all I have to do is to integrate the last two variables away, and I will get the volume. Well, let's try to produce a recursion for these functions. So let's do fn plus 1, and then the last variable is xn and xn plus 1. Well, definition is we integrate over n minus 1 variables, chi n plus 1, x1, all the way to xn plus 1, dx1 over to dxn minus 1. And now I'm going to break the integral up to two integrals, one integral fashion 1 0 to 1, and 1 over, so I'm confusing myself, 1 over n minus 2. And now, as I said, that function chi n plus 1, it factors. Namely, it's a chi function in variables, x1 for xn, times the chi free function on the last three variables, n minus 1 and n plus 1. What is it factor? Well, my condition is that I don't want any double ascents. So this guarantees that on the n variables I don't have any double ascents, and this guarantees on the last three variables no double ascents. So that actually rules out if a double ascent occurs, that will be here or here. And now we can integrate, well, dx1 to dxn minus 2, and finally, so that's that integral, and finally dxn minus 1. But now, the nice thing is that the variables occur here in the function of three variables are not integrated by the n minus 2 first variables. So this term goes in here. So we get integral 0 to 1 chi phi xn minus 1 xn plus 1 times, and now you see what's left. That's just the function fn of the previous two variables. Dxn minus 1. Isn't that nice? This gives a recursion. From this function, we integrate and we get out this one. In fact, it's a linear operator. We have a linear operator t for functions in two variables and on the unit square, two variables, to itself. And this is defined by t of x, y is equal to integral 0 to 1 chi txy times f of dx dt. So you notice that the n function, what is the recursion? What is the starting thing? The starting condition is that f2 is a constant function equal to 1. So So the n function, I have to divide this operator n minus 2 times to that function. So that means the number I'm looking for, I can express it as alpha n over n factorial. I just have to integrate away 2 variables away. One way to say that is that I'm just applying the inner product with the function 1. I just integrate the last 2 variables away. This is an operator raised to some power. So the way we should study it is to understand the eigenvalue of this operator. But before we start looking at that, let me make this operator a little more explicit. Namely, let me say that the function, let's divide up in 2 pieces. Pxy for x less than y, and q of xy for y less than x. I know it's a function of the unit square, and I'm just cutting it here. X, y is the p function, is the q function. So let me write it down more explicit what happens. So t of x, y, I can look at these cases x less than y and y less than x. So notice one thing, I don't care what happens when x is equal to y, because that's something of measure 0, so we don't have to worry about that case. So now, when x is less than y, that means that if t is less than x, I get a double ascent here, I get 0. So hence, I don't have to integrate, I get 0, I can throw that away. So I'm only testing the case when t is greater than x. And then I'm integrating over t, so it means I'm integrating t from x to 1. Then this function, type function is 1, and I have t is greater than x. That means I have to go and put in the q part. So I get q of tx dt. Now to the next case, y less than x, x greater than y. Well, if x is greater than y, then I'm never going to have a double ascent in here. So this function is always going to be equal to 1. The only thing I have to be careful is which I'm using the p or q part. Well, I have to check if t is less than x or t greater than x. So if t is less than x, that means I'm integrating from 0 to x. T is less than x, this is p. So the p of tx dt. And then I have the other case, t greater than x, and that's going to be like the previous case. So I get from x to 1 q of tx dt. So there's the operator explicitly written. So now we can start looking for eigenvalues. So I want to solve lambda xy is equal to t of fxy. So the equations comes out to be lambda qxy equal to integral x to 1 q dx t lambda qxy is equal to 0 to x, q tx t plus x to 1, q dx t. Well, if you look at the system now, a very nice thing occurs. Notice there's no y on this side. And there's no y here either. So it tells that the eigenfunction is not going to depend on y. So really, the second variable in the function p and in the function q just drops. So truly what I have is just that lambda p of x equal to integral x to 1 qt to t, and lambda q of x from 0 to x q of t to t, that's the same thing here, x to 1 qt to t. So we had a problem on this unit square. I now have that this only depends here, the function p only depends on x, and the function q only depends on x. So I've now got it into a problem finding two functions in one variable each. So this is now a problem you can give to your Calc 4 students to solve. On the second thought, don't give it to your Calc 4 students, okay? And then, so you have to solve, what do you have to do? You have to take derivatives, so you get lambda p prime is equal to p prime of x. Take derivative, I get minus q of x, lambda q prime of x is equal to p of x minus q of x. And you start working out the details, you solve this diff equation. But the important part is that you go back to this equation system for the boundary values. Because you see nice things like, for the x equal to 1 here, the integral vanishes. And and you're looking for non-zero eigenvalues. So you get that p of 1 has to be 0. And similar things down here. So you start working that out. Let's skip the details. So you get the eigenvalues. Lambda k is equal to square root of 3 over 2 pi k plus third, where k is the integer, and the eigenfunction itself, phi in terms of xy, e minus x over 2 lambda, lambda is the eigenvalue, times cosine of pi over 6 plus square root of 3 over 2 x over lambda is for x less than y.
There's no y, right? So
Well, there's no y in the function, but it's y here. I mean,
yeah, p and q.
Okay, I lost my unit square, but and sine pi over 3 plus the same thing here, square root of 3 over 2 x over lambda, which is y less than x. However, there's one problem. I was born and raised in finite dimensional vector spaces. And now, this is on the L2 space of the unit square. So even though I have eigenvalues and eigenfunctions, what does it tell me? I mean, you had to go speak with function analysis to find out does this actually tell me something about the log behavior of the t applied to the function 1 several times over? So the thing that saves us is, let's look at the operator squared. What happens when I apply that to the function? Well, I can add the shift operator twice. So I get two integrals. Chi stx, saying I should avoid any double ascents with these. No double ascents on t xy times the function f of t ds dt. And now look at this. This has a very nice form because this looks like matrix multiplication. Well, this usually matrix multiplication is a sum. What are we summing over? Well, this S and T. This is the matrix. And this thing here is the vector. This is a nice looking operator. In fact, it tells you that this is a Hilbert-Schmidt operator. So it's something that's well studied. Because the problem with the operator that I had was that this shift in it, that it was, I had Tx here and I operated one way. And I asked people to look for it and no one's showed me somewhere they have found that operator. But operator T squared is Hilbert-Schmidt, which means it's a compact operator. So you can go and read in the literature. And the nice thing is to say everything you want, you can work things out with compact operators. Furthermore, if an operator whose power is a compact operator, the spectral field is going to work for that operator too. So we're on safe ground. Luckily. Well, then, theorem, and now you can sit down, do your analysis, and prove a result like this, that lambda 1 lambda k be eigenvalues of t larger than r in modulus. I am in the complex plane, and I want all the eigenvalues as far as possible away from the origin. Assume that these eigenvalues are simple. I don't want any problem with Jordan canonical form. Let Ci be the associated eigenfunctions, and let the Psi be the eigenfunctions of the adjoint operator, which I'm also going to need here.